Okay, so Calc 3 is basically the calculus for physics. This class exists for the physics world. You say, well, what about Calc 1 and 2? So I want to make sure everybody understands what's going on here. First of all, the calculus sequence at Mesa College, it's basically the Lord of the Rings trilogy. It's one big movie that we split into 3 parts. The first 2 semesters, you are mastering the calculus of 2 dimensions, real valued calculus. And what I mean by that is real valued calculus means all of our inputs and all of our outputs of functions are real numbers. We do not do complex numbers in calculus outside of just the hyperbolics. That's the only place where we ever run across complex numbers in the calculus context. Calc 3 is the calculus of 3 dimensions. So really, it's everything you did in Calc 1 kind of translated down to 3 dimensions. We do very, very little Calc 2 in this class. That surprises people. Calc 2 is really the prerequisite for Math 255, differential equations, because that's all about integration. This class, differentiation is far more of a main thing, and mastery of vectors, okay? Because we're looking at, again, the physics. And so why is this class important? Because you live in a 3D world. It's actually that simple. Doing math in 2 dimensions exclusively is very limited and not really real. It's kind of artificial. Now, what about the complex numbers? Well, Calc 1 and 2 is real valued calculus in 2 dimensions. Calc 3 is real valued calculus in 3 dimensions. And then as an upper division course, there's something called complex analysis, which is the calculus now with complex numbers. And that, if you're an engineer, you're probably taking that one next year. If you're San Diego State, I think it's Math 537. That's a major course for engineers. Some math folks take it, but it's definitely engineering related. So we're going to start off with vectors. Now, many of you have had linear algebra, I know that. The way we look at vectors in linear algebra is very different. We take a much more theoretical approach. And in linear algebra, we're looking at vectors in n dimensions. In other words, we are not limited by the 3D world. Everything is 2 dimensions, 200 dimensions, it doesn't matter. We establish all the rules that are true in general. But Calc 3, we spend most of our time very specifically talking about vectors in 3 dimensions. So there's a lot more algebra and application in this class than there is in linear algebra. So again, we're not going to contradict anything we do in linear when you put the 2 together. Again, linear is far more theoretical. This class is far more application of vectors. The first month of the semester is pretty low-level, simple vector stuff. Now, I've taught this class for about 1 million years. I taught it ever since Professor Newton gave me permission to start sharing some of this stuff, a few hundred years ago. I found that if you have physics, you've been exposed to vectors, and it also means you have a long list of extremely bad habits. In other words, it's quite likely that a significant amount of the vector algebra you do is not even mathematically valid. We do some of the craziest things that are not actually mathematically possible, but we got an answer because that's what they did in physics. We're going to do things correctly, and you're going to find when you do things correctly, absolutely 100% of the time, it's going to be easier. You're not going to be bound by some really weird way of doing things. If you've never had physics, and this is your first exposure to vectors, you're not under any disadvantage because we're starting from scratch. Now, first of all, what the heck is a vector? Well, first of all, there's 2 ways to look at things. Okay, and now I'm in a 3D world. So I say, I'm going to turn in a particular direction. I want you to go in a general that way direction 100 feet. I'm pointing in a direction. I've just created a vector. I gave you a direction and a distance to travel. I gave you a finite distance in a direction. So first of all, it's a line segment. It's not a line. It's a line segment, and it's got a direction. So a vector, we say, is a directed line segment. The line segment implies that it is finite, but the direction matters, because if I start here and I go 100 feet in that direction, that's different than starting at the end and coming 100 feet this way. That would be a vector pointed in the opposite direction. So direction matters. So there's only 2 things about a vector: direction, length. Okay? The word we use for length generally is magnitude. And the reason we use magnitude rather than length, because a vector might represent some physical units. Like, for example, the vector might represent velocity, acceleration, force, So in other words, the length of the vector might be 10 units long, but is that 10 meters? Is that 10 miles per hour? Is that, 10 pounds? Whatever units you're using are the units you would apply. So rather than say length and direction, we say magnitude and direction, because magnitude implies there are units. Length implies there are only length units. So you can't really get velocity if you only have length units. So it's a directed line segment. So that means there's magnitude and direction. Okay. Now, if I'm in the real world, and I point this out to people all the time, they seem to have trouble with this, there is no XY plane on the floor. There is no XY plane on the floor and the Z axis running vertical when I go outside. See, when the plane is flying around in the air, there's not some big three-dimensional set of axes that you can clearly look at. I'm going 10 in this direction, 20 in that direction. So in real life, we describe vectors only one way, direction and magnitude. But when I want to do the mathematics of a vector, when I want to combine it with other vectors, when I want to solve that problem in physics, where I've got, you guys have done that with the pulleys and the cables in different directions and different weights, I need to be able to orient it to a set of axes. So we also describe vectors as they look on the XY plane or XYZ space. And so for the algebra vectors, we use that representation knowing we can easily go back and forth. And over the next couple of days, we're going to establish how you go back and forth. So I'm going to do most of the analysis today on the XY plane because I can draw pictures. Knowing that what's true in 2 dimensions isn't necessarily automatically true in 3 and vice versa, but it makes for an easier explanation. Now, the first rule is whenever you're giving a vector and you're giving an algebraic interpretation of a vector, all vectors start from the origin automatically. Now, here's the problem with this notation right off the bat. I'm representing a vector. In geometry, what do we call a line segment with the arrow on the end? Does anybody remember? You can blurt it out. What's that called?
I think it's a ray.
It's a ray. And how long is a ray?
It's infinite in one direction.
It's infinite in one direction. Yeah. So right off the bat, we confuse ourselves with using notation that means if that's a ray, that means it's going in this direction forever. If that's a vector, it means it's starting here and it's physically ending here. And that can be confusing. So I'm going to make it really clear. We don't use rays when we're discussing vectors. We're only doing finite. We don't use infinite vectors. We use finite directed. And the directed means the arrow goes here because I could also have the arrow go that way. So let's say on the XY plane, that point is A comma B on the XY plane. We call that the terminal point of the vector. So I'm going to give you the different representations of the vector because the one thing we want to be in agreement is in how we represent something. Because if 2 people represent the same thing differently, then that can be confusing. You're going to write a report for your job and you represented things a certain way, but the person reading it is interpreting it some other way because they didn't use your representation. That's a problem. So first of all, we'll call this vector V. So when you're writing a vector, you generally give it a little hat. Now, what I mean by a hat is that's a partial, that's not an arrow, that's a hat. And the reason we use that notation is because when I'm indicating something as a ray, I actually do put the arrow. So if you have an arrow over this, that is how you indicate that it's a ray. It's only partial arrow, so that indicates that it's a vector. The difference is when you're writing by hand, you put something over the vector to indicate it's a vector. When you're printing it, you don't put something over it, you just print it bold. Okay, and again, that can be confusing, but every textbook written, if they're talking about vectors, they'll just represent it with bold print. When I'm giving you work and I'm representing a vector, I just do it using bold print. But when you're writing, you don't want to go like this. Okay, here's my vector. That's kind of ugly. So we just represent it this way. And then the notation we generally use is that type of bracket. The terminal point of my vector is the point AB. AB is an address. It's a point on the XY plane. This represents the physical object. This is the entire vector. A vector is not a place. A vector is not a value. A vector is a thing that has measurement. Now, what is the measurement? Well, the measurement is how long it is And the direction in the XY plane, we'll usually use the angle made with the x-axis to help us give a simple direction. So that's it. I mean, that's not very exciting. Now, in 3 dimensions, we do the same thing. It's just that we're moving in 3D, so we would have 3 components, A, B, and we'll call it C. So starting with that, now what can you do with vectors? Well, right off the bat, vectors only have 2 defined operations, addition and scalar multiplication. I will make reference to linear algebra all the time because I know a lot of you have had linear algebra. Some of you might be taking linear algebra this semester, and many of you will be taking it later. But that's a class that people often double up. And the terminology we use is exactly the same in the 2 classes. So I want to make sure everybody understands that. So the only 2 operations are addition and scalar multiplication. If you've ever worked with matrices, okay, so maybe in baby algebra, there's exactly 2 operations, addition and scalar multiplication. You say, well, what about matrix multiplication? No, that has to be defined. In other words, I'm literally making it up. I'm saying, okay, I'm going to define this new operation and it's going to be this way, and then it's consistent and there's no problem. But naturally speaking, you can add them, you can multiply them by scalars. So if I can add 2 vectors, well, right off the bat, let me define a vector, we'll call it W, and W is an element of Rn. So I'm going to give you some notation. Now, if I just make a script R, that refers to the number line. That's the set of real numbers. R2 is the XY plane. R3 is XYZ. And this comes from something called a Cartesian product. And if anybody's had discrete, or some of you are in my discrete class, our Cartesian product is where I say I've taken the real numbers, crossed with the real numbers, crossed with the real numbers, now I have an ordered triple. The real numbers crossed with the real numbers, now I have an ordered pair. So I'm going to cross the real numbers with the real numbers n times. I have an ordered n tuple. So that means that W looks like this. W1, W2, dot, 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 Wn. This is the formal standard way of representing any vector. I said in our class, we're only looking at 2 and 3 dimensions, but understand that vectors are not limited by dimension. So that's the standard way of writing it if it's in that dimension. So the first rule of vector addition, it's a simple rule, but it's an absolute. And you can only add 2 vectors that are in the same dimension. Okay, I cannot add a 2-dimensional vector to a 3-dimensional vector. That operation does not exist. So if I said, let's consider vectors u and v are elements of R, excuse me, of R2, because I can draw the picture. Then we'll define vector u, let's say, to be u1, u2. Let's define vector v to be v1, v2, where u1, u2, v1, and v2 are just simply real numbers. Now, here's a whole nother issue. Vectors are not limited to real numbers. In fact, if you've had linear algebra, hopefully you spent some time discussing complex vectors, because the way of the world, actually, there is no such thing as a restriction on whether things are real or complex. The farther you go in mathematics, you realize everything involves complex numbers. But we've only been dealing with real numbers. Yeah, you're dealing with numbers where the imaginary part was 0. But there is no such thing as a restriction in general. And so we're only looking at problems right now where there's no imaginary stuff. But in general, a vector can have imaginary numbers. It can have any form of complex number as its components. There is no restriction. We are going to avoid those in this class. But when you get to linear algebra, you're going to discuss the complex versions of the vectors. And so it's very important to understand there are really no restrictions the farther you go. So the u1, u2, v1, v2 are elements of the real numbers. So I'm only dealing with real number calculus today. So now the next thing is I'm going to define u plus v triple bar. This is a symbol many of you are not familiar with. If you've been in my classes, you've seen this because I use this symbol. 3 bars means is defined as. It does not mean equals. Is defined as is far more powerful than equals. Equals is a result. When you're defining something, that's different. You don't have to prove a definition. When you look a word up in the dictionary, you don't say, well, why is that the definition? Nope, that's the definition. You got to live with it. You have used this symbol before and you may not have realized it. I'm going to give you a couple simple, really simple analogies to help you remember. On the unit circle, This is the unit circle. The cosine of theta is defined to be x. The sine of theta is defined to be y. It cannot be calculated. You can't calculate the sine and cosine of theta. You have to define them first. And then once I define them, I can calculate them. And the tangent of theta is defined to be y over x. Oh, but wait a minute. If it's y over x, wouldn't that be the same as saying sine over cosine? Yeah. So y over x is equal to, not defined as, this is a result of this definition. So the equals means it's a result. I'm going to define the addition, and then from there we can do things after the fact. The other place that everybody's quite familiar with, if I said, can you calculate the square root of -1? No, but what do we know it is? We know it's I. Why do we know it's I? Because that's the definition of I. I is defined as the square root of -1. It cannot be calculated. That's the definition. But from that definition, if I said, then what's the square root of -4? You'd say, oh, that's equal to root 4 root -1. So that's equal to 2i. I can calculate this based on this definition and the fact that it's a square root. So when something is defined, it's beyond question, but then you use that definition to answer further questions. So with that being stated, this is a really complicated definition here. Given this definition of U and V, that it's U1 plus V1, comma, U2 plus V2. And by the way, this definition is the same in higher dimensions. So if I took two n-dimensional vectors, I'm basically adding the corresponding components. That's what we did here. So the definition of vector addition is you have a vector where you've added the corresponding components. So one of the first, and actually the single most important characteristic of vector addition is, what do you notice about your result? It's still in R2. Because I still only have two values. These are both real numbers. This is called closure. Okay, and that is far and away the most important property anytime you're manipulating things. Is the concept of closure, quite simply, is if I take two elements of a set and I combine them using whatever you're talking about. In this case, it's addition, but I could do something else. If I take two elements of a set and I combine them, if my result is always in the set, then we say the set is closed relative to that operation. So vector addition, we say, is closed. If I take any two vectors in the same dimension and I add them, I get back a vector in that dimension. That is huge. It's not an automatic thing. Okay, getting back something in the same dimension is not the same. For those who remember matrix multiplication, when you multiply two matrices together in a legal multiplication, your result is usually not the same shape as the original matrices. And so the closure is not automatic. Now, what you also notice about this, U1, V1 are real numbers. And I know that real number addition is commutative. I know then that this statement is true because real number addition is commutative, but wouldn't this therefore be we've just formally proved that vector addition is commutative. Oh, well, that's kind of cool. Isn't that automatic? Isn't everything commutative? Actually, there are very few operations in mathematics that are commutative, strangely enough. Okay, we're going to be looking at things in this class, but I'll use something like matrix multiplication. We know is not commutative. We're going to, next day, we're going to talk about something called cross product. We know that's not commutative. In fact, in general, the quotient rule in calculus is not commutative. Okay, most things are not commutative. Vector addition is commutative. In fact, it's also associative, which makes things really nice. Now, let's give this a physical interpretation. Because this can be very useful. We're adding these vectors, but we don't even know what they mean necessarily. So let's say this is vector u. Let's say this is vector v. Let's just keep it real simple. My resulting is a vector where I've added the components. The resulting vector, turns out, would be equivalent if I took the u and I attached it to the end of the V, or I took the V and I attached it to the end of the U, in either case, this would be my resulting vector. So whatever U1, U2, V1, and V2 were, this vector that's the vector of the sums would be the equivalent of just piecing one and slapping it onto the end of the other. So that's what vector addition always results in, which is very nice. Now, real numbers have exactly 11 properties that we associate with algebra, okay? So let's start with addition. Let's keep it real simple. Real number addition, commutative, associative, there's an identity, there's an inverse, and it's closed. Meaning if I add any two real numbers, I get back a real number. Real number multiplication is commutative, associative, there's a multiplicative identity, a multiplicative inverse, and it's also closed. And the 11th property is the distributive property, which is adding into and product, right? You're multiplying a sum. There's 11 properties of real numbers that we associate with the algebraic properties. How many of these are true for vectors? Now, if you've been in linear algebra, you remember the rules of a vector space, for example. There's 10 algebraic statements. But really, we'd like to know which of the algebraic properties of real numbers translate exactly to vectors. For example, vector addition is commutative, it's also associative. Beautiful. But what about things like identity and inverse? Identity and inverse, those are actually really important concepts. Generally in mathematics, identities and inverses kind of go together. You don't really think of them as being independent things. So an example might be, my function in life is I go around and I tie shoes, okay? Viet goes around and he unties shoes. He's my inverse. An inverse mathematically is any operation that undoes another operation. So I see your untied shoes, I visit you, I tie them, and then Viet visits you and he unties them. What is your final state? As if nothing happened. An operation took place and there's no change. That's called a mathematical identity. An identity is when an operation takes place and nothing changes. So when something and its inverse both act, the result is if nothing happened. So in algebra, right, think about addition for a moment. I brought my checkbook today and I'm going to write every single person in here a check and I'm going to sign the check. And I'm going to make everybody here a check for $0, and then I'm going to hand you it. So if physical action took place and your overall well-being is exactly the same, okay? That's because I applied the additive identity. Is there a vector that acts like an additive identity? So a vector U is U1, comma U2, and let's say I have a vector, we'll call it W this time. Here's what I want. I want U plus W to equal, is there a vector that acts like an additive identity? Well, let's see, what would this be? According to my definition, this would be U1 plus W1 comma U2 plus W2, and I want it to equal U1 comma U2. Well, how can U1 plus W1 equal U1 unless W1 equals 0 and W2 equals 0? Oh, I think we figured it out. There is an additive identity of vectors. There's clearly an additive identity of vectors. And what would it be? The vector of zeros. We have a very clever name for the vector of zeros. Anybody remember what it's called? It's really cool. You'd never figured this out, though. The vector of all zeros is called
The zero vector?
the zero vector. Good. Okay. Yeah. It's the only we're probably going to have today. Yeah. Remember, in math, when it comes to naming things in math, we're not really very creative. And the theorem that does this is usually called the theorem that does this theorem. Arguably the most important formula in all of mathematics outside of calculus, believe it or not, the most used formula, because we use it in Calc 1, 2, and 3, as well as linear algebra, differential equations. It's when you have a point and you have a slope and you want the equation of the line. Remember that one? It's called the point slope formula, because after 3,000 years, that was as clever as we could come up with. The rule for finding derivatives of products is called the product rule. You see where I'm going with this? The only thing we didn't like was something like Simpson's rule in Calc 1, because what the heck is a Simpson? We don't like it when theorems are named after people. We like it when the theorem is exactly what it is. So the zero vector is the vector of zeros. And generally speaking, we often write it like this. Now, the problem with writing it in this way is that does not indicate dimension, does it? See, what if I had 3 zeros or 5 zeros or 13 zeros in my vector? Those would all be called zero vectors in their particular dimension. Now, here's the nice thing. If I'm working with vectors in 2 dimensions here, there's no possibility I'm going to introduce another dimension within the problem. You can't. That means we're living in a 2-dimensional world while we're doing all of our math today. So the zero vector has to be in the same dimension. It can't come from a different dimension. But in general, when I'm trying to establish rules of vectors that are true for all dimensions, then what we often do is this. Really clever. I put a subscript there to indicate that's the 0 from R2. In this context, there's no way you're going to misinterpret what dimension we're in. But in general, if you opened up a document, started reading, and you saw the zero vector, but you didn't know what dimension it was, that could be a problem. So right off the bat, by putting the subscript of 2, I'm indicating it's the 2-dimensional zero vector. And in linear algebra, when we're doing things like, changing bases and we're doing linear transformations of things, we often do change dimension. So you might have a zero vector in 2 different dimensions within the same context. And we definitely want to keep these clear. Now, if there's an additive identity, then there must be an additive inverse. All right, so what does that one look like? Okay. Well, first of all, I'm going to define something called scalar multiplication. In math and physics, we use words like scalar, but that sounds very powerful. But what the heck is a scalar? A scalar is a constant, but it's not just an arbitrary constant. See, in calculus, when you integrated, didn't you always put a plus c at the end? And we called that the arbitrary constant, but we don't call that a scalar. That is not a scalar. A scalar has to be a coefficient. It has to be a multiplier. And I like to think of it this way. If you're looking at a map, okay, you go to, I go to Google Maps all the time. I have that as one of my favorites because I need directions everywhere I go, and yes, I do print the directions everywhere I go, right? And so it's that funny commercial about you becoming your parents. You guys seen that one? It says, if you printed directions, then you're in the right place. And my wife and I look at each other and go, we always print the directions, otherwise we're going to get lost. So I go to Google Maps and I'm looking at San Diego, or I'm looking at California, I'm looking at the United States going, wow, the United States doesn't look very big. It's only like 10 inches wide. I thought the United States was really big. Well, then you'll have a little thing called a legend at the bottom that will say, 1 inch represents what? A mile, 10 miles, 100 miles, 1,000 miles. That means that's the scale you're using. So you would have to scale up or scale down your picture by multiplying by the appropriate number. That's what a scalar is. That's where the word comes from scaling up or scaling down. If your scalar is 1, then you're not changing anything. So scalar multiplication is defined this way. For any real number k, and again, this could be complex, but we're not doing complex vectors right now. And let's go back to u being u1, u2. Then ku is defined to be ku1, ku2. Okay? A scalar multiple is when I multiply a vector by a scalar, I multiply each component of the vector by that scalar. That's what it means. That's it. It's not clever. It's not cool. So if I said 2 times the vector, that means we just simply double every component. If I said -1 times the vector, that just means we change the sign of every component. That's it. Now, with that statement there, now I want to ask the question, using this u right here, I want a situation where u plus v equals the 0 vector. I want the additive inverse because we've already declared the 0 vector as the additive identity of vectors. So now I want to find what is the additive inverse of any given vector. Well, according to what I have, this means that u1 plus v1, comma, u2 plus v2 is equal to the vector of zeros, which would mean that v1 must be the negative of u1 and v2 must be the negative of u2. So vector v would be negative u1 comma negative u2, or more simply negative u. Negative u is the same as negative 1 times u. So every vector has an additive inverse. It'd just be negative 1 times that vector. That's just like real numbers. So right now, the 5 properties of real numbers that apply to addition: closure, commutativity, associativity, additive identity, additive inverse, all 5 of those properties apply to vectors. That's very comforting. And the reason that kind of stuff is so important, again, I'll make the linear algebra reference. If I show that a certain set of things, could be the set of real numbers, the set of matrices, the set of polynomials, whatever. If the set of things has a bunch of inherent properties, and I come up with another set of things that's completely different, but I can show it has all the same properties, then conclusions I make about one, I can also make about the other. Whoa, that's really cool. So again, that's, if I can show that vectors have properties of real numbers, then some of the conclusions I make about real numbers, I may be able to make about vectors, which is really nice. Okay. Now, we don't have a vector multiplication. We don't have functions of vectors defined. You can't take the cosine of a vector. I can't say a vector raised to a power. I can't take the square root of a vector. I can't cube a vector. I can't take a quotient of vectors. Nope, I can add 2 vectors. I can multiply a vector by a scalar. For right now, that's it. We will define other things later, but those are the only 2 operations that are automatic. Again, addition and scalar multiplication, and you'll find that across mathematics, they're the same 2 over and over and over again. In fact, from a calculus standpoint, if you think about limits, the limit of a sum is the sum of the limits, the limit of a scalar multiple is the scalar multiple of the limits. Those were the only 2 that applied to derivatives. Derivative of a sum of the derivatives, derivative of a scalar multiple, the derivative, and then they applied to definite integrals. Integral of the sum of the integrals. So in other words, sums and scalar multiples are the 2 properties that, or I should say 2 operations that apply across the board to other things. So very, very important. So let's do a simple exercise here. Let's suppose that I say vector u is 4, -3, 2, and vector v is 5, 6, -1. I want to find 6u minus 4v. Now, I'm asking you to do something called a linear combination. I'm introducing some vocab here. This is what is called a linear combination, because I'm taking scalar multiples and I'm adding them. I can do this with anything. I could do this with polynomials. I could give you 2 polynomials and say, hi, I want 6 of one minus 4 of the other. I could do this with integrals. I could do this with derivatives. So my final answer should be a vector in R3, because I'm starting with vectors in R3, and scalar multiplication as well as addition preserves those, meaning they're closed. So the simplest way to do this is start by multiplying the first vector by 6. So I'd have 24, -18, 12, and then multiply your second vector by -4. Now, I know most of you would say, no, I'm going to multiply it by 4 and then I'm going to subtract. And exactly half of you will get a wrong final answer. I know this because I do this all the time. Why would you subtract 2 vectors? You're only going to remember to subtract the first terms and forget to distribute the negative sign. Bad algebra. So just multiply this by -4. So -20, -24, +4. So my result is 4, -42, 16. Because you were just combining things algebraically and you were not solving, you really can't check. There's nothing to compare it to. So you just have to be careful. And what I meant was, when I said don't subtract, what I find that most people will do, they'll subtract, right? And they'll say, okay, that's -20, 24, and -4. And then, as we know in algebra, you're all going to subtract the first term and then add all the rest, because that's what people do. Whenever they have to distribute a negative, the negative generally only makes it to the first term and doesn't make it to the rest. This is about as low-level arithmetic as you're ever going to see. You can't make mistakes on it. This is just too darn easy. Don't make up more steps. So that's the answer. That's it. Not very exciting. but this is one of our first manipulations of vectors. Again, not terribly exciting, but because of this, now we can do other things. So now let's go to the next level of things. All right, let me go back to my two-dimensional picture. Okay, this is vector V, and we're going to call it A comma B, lack of a better name. So if I made a right triangle here, then I know that this side would be length A, this side would be length B. Okay, it's really not all that complicated. I'd like to know how long is this vector. Well, that's just simple Pythagorean theorem. Okay, I know how to find the length of that vector. But what is the length of that vector? What is that called? That's called the magnitude of the vector. And the symbol we use for the magnitude or the length, in this case, same thing, it's double bar. And a lot of you have seen this notation elsewhere. Certainly in the Riemann sum in calculus, when you're first starting integration, you see the two sets of double bars. In every context where you see two sets of double bars, there's another word for it we often use, norm. Okay, if you've heard the term norm before, norm and magnitude mean exactly the same thing, just fewer symbols or syllables. So this is the norm of V. I'd rather say the magnitude, it's more specific to my point. What it is not, and by the way, many textbooks make this mistake, and TAN does this. A lot of textbooks will put absolute value. That's actually a gross mathematical error. Sorry, gross doesn't mean disgusting, it means astronomically large. Absolute value is only defined for complex numbers. It's a real number is a complex number with zero imaginary part. Absolute value only applies to complex numbers. In other words, first of all, absolute value only applies to something that's unitless. Absolute value cannot apply to vector. The absolute value of a vector makes no sense because a vector is not a number. A vector is a physical object. That'd be kind of like saying, okay, I want the absolute value of Josue. What's the absolute value of Josue? Pick something, the number of teeth in your head, the number of hairs, your weight, your age. No. Those are called measurements. Those are not absolute values, and those have units. Absolute value is how far am I from the door? How far is the door from me? Absolute value is always a distance between two things. So absolute value is take a point on the complex number plane and find the distance to the origin. And it's unitless. So I always drives me crazy when I see people do this in calculus. No. I don't care if your textbook did that. That doesn't mean the same thing. This means magnitude or norm. Now, going back to my picture, isn't that just simply going to be this? Now that is a scalar. So here's the reason this is important. We find length of a vector for many reasons, not just because we want to know the magnitude, but it's like this. So I'm going to say, Sam, I need you to go in a general that way direction. Starting from where I'm standing, I want you to go that way. Now, here's the first thing. How far is that way? Technically, how far is that way?
I guess infinite.
Infinitely, yeah. So we have a problem right now. You're going, how far do you want me to walk? No, I want you to go that way, and I want you to go 100 feet. Beautiful. But that way is infinite. So really what would be more useful to you is if I make that way of length exactly 1. In other words, make a vector of exactly 1 in a that way direction, and then multiply that vector by 100. Now, wouldn't I have my 100 unit vector in a that way direction? Yes. So when I say that way, technically, I want you to go west, young man. How far is west? West is forever. You just keep going. Oh, I want you to go west 100 feet. Okay, that's different. So let me get my direction. Let me make it of length 1. So I would like a vector in this direction that's exactly 100 units long. How do I do that if this is not already 100 units? What I do is I first make a vector in that direction that is exactly 1 unit long in that direction. And then I take that and I multiply it by the scalar that I'm interested in. So how do I make that vector of length 1? Well, that vector of length 1, first of all, is called a unit vector. A unit vector is a vector of length 1 in whatever direction you started with. I want a unit vector in the direction of v. Well, how do I do that? If my original vector was 27.3 miles long, how do I make it a unit vector? By multiplying it by the reciprocal of 27.3 miles. If I have a vector that's 10 units long, then multiply it by 1/10. Does that make sense? Oh, okay. Because if it was 10 units long and I multiply by 1/10, now it's only 1 unit long. You notice I said multiply it by the reciprocal of its length. Well, why don't I just divide it? Because there is no such operation with vectors. The word division and vectors do not come into the same universe. Again, for those who've had linear algebra, you go into far more depth and detail of these things. You see, I'm going to give you some absolutes, and people love absolutes in math. If A over B exists, then B over A exists, period. It doesn't even matter if one of them is 0. We say, well, what if it's 0 over B? Well, then it just means that's undefined, but undefined is still a valid answer to a mathematical question, because if I ask you what's the slope of a vertical line, don't you tell me it's undefined? In other words, you say, well, you can't divide by 0. No, you can't represent a final answer as a quotient of 0. We divide by 0 all the time. We get to complex analysis. By the way, you've all heard, Chuck Norris can divide by 0 and he counts to infinity. I taught him how to do both. He counts to infinity. You count by 10. You can get there faster. And the divide by 0 is a parlor trick that you're going to learn in complex analysis. And I'm not joking. You learn to work around things. That's not even an issue. It's an absolute mathematical statement. Anything that appears in a numerator, absolutely without any restriction whatsoever, anything that appears in a numerator can also appear in a denominator. There is no exception. So if you're going to take a quotient of vectors, then you're saying a vector can appear in both a numerator and denominator. Therefore, I can have a vector divided by a vector. I can have 1 divided by a vector, which, by the way, those operations don't exist. A vector cannot appear in a quotient. There is no such mathematical operation. So just to let us know, if you look at some of the videos, I go over that. So how do I represent my unit vector? My unit vector is 1 over the length of v times v. That's it. That's my coefficient. That's a scalar. Now, if I don't want to leave it in that form, we'll do some with some specific values. So if I don't want to leave it in that form, I just simply multiply it in. So let's take a really, really simple example of this. Find the unit vector in the direction of how about, I'll call it U this time. U is UB, UR, I know, bad English all over the place. Let's say I want to find the unit vector in this direction. So to be in this direction, it must be a scalar multiple of this. Remember, a scalar multiple, I'm taking the vector and I'm shortening it or lengthening it, but it's still going to be in the same direction no matter what. So I'm just going to take a scalar multiple of this. Well, how do I find that scalar multiple? I start by finding the magnitude, which is just going to be the sum of the squares under the square root. So 36 plus 4 plus 16, okay, 56. Now, when it comes to square roots, it's always better to deal with smaller roots. So if I can reduce this, I should, because it'll make my life easier later on. I think I can break this down into root 4, root 14. So that's 2 root 14. Okay. So now what is my unit vector? It's 1 over 2 root 14 times 6 negative 2, 4. Now, I'm just going to multiply that in. Well, let's see. I can do a little bit of canceling. So 3 over root 14, negative 1 over root 14, 2 over root 14. Now, since I can't simplify this any further, this is a totally acceptable answer. For those of you who have been conditioned, you can't ever have a root on the bottom and pain and suffering will come your way, then yeah, go ahead and rationalize it if you want. You don't have to. I've simplified. Simplify means there's no common factors top and bottom. Okay. My experience is, in all the years I've been teaching mathematics, I've never actually had a student who knows what it means to rationalize, so I would leave it alone. So wait, don't you want to put the root on top? That's not rationalizing. That's not even like rationalizing. I want to remind people because, first of all, this is a perfectly acceptable final answer. And I know a lot of you say, I can't do that, I can't do that, I got to keep going. If I said 1 over root 2, we know that's equal to root 2 over 2. We know that's equal to 1/2 of root 2. Do a quick check. If that were your final answer, we do this with sines and cosines all the time. That's okay. That's okay. That's okay. That's the only one that's rationalized. That's not rationalized. And anybody who told you there was, they're trying to get your money. They're trying to deceive you. The term rationalized means there is no root in the quotient, period, numerator or denominator. Rationalize means there's no root in the quotient. And the reason we rationalized for many, 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 many years is that we didn't have one of these. Believe it or not, there was a time when you were working with roots and logarithms and things, you had to look in the back of the book, they had tables. Maybe the integers 1 to 100 and they had all the square roots to 3 or 4 or 5 decimal places. And then that's what you used. And then you did that. Oh my God. So I'm in a math class and I have this and I have to give a decimal for this. Doing long division of decimals, you remember how evil that was? Well, the reason you rationalized is I could look up the number in the back of the book and then just take half of root. Oh, that's so much easier. But since calculators were invented and became commonplace, there's no reason to rationalize as a means of saying it's an easier answer to deal with. You only rationalized because the decimal conversion was too difficult by hand when you had a root on the bottom. Now, there is still a reason to rationalize. There is one reason and one reason only, and it does come up occasionally. I'll show you why you still want to be able to rationalize. I've got, how about 3 over root 2 plus, I don't know, something ugly. 5 over root 32 minus 1 over root 8. Okay, that just looks hideous. Here's why you learn to rationalize, because I'd like to write that as one thing. How do I do that? Well, that's 4 root 2, and that's 2 root 2. So if I multiply top and bottom here by root 2, root 2, root 2, and I do the same thing here, then this will become 3 root 2 over 2. No, it'll become 3/2 root 2. That's rationalized. Plus, sorry, that's root 2. This is 5 root 2 over 8, or 5/8 root 2. This one, root 2 over 4, or 1/4 root 2. So my final answer is 3/2 plus 5/8 plus 1/4 all times root 2. Oh, now I'm just going to use my cheap calculator. I can do this in my head, but I just want to show you. I don't want to do any work. I just want to, I'm sorry, that was a minus, not a plus. Oops. Let me go back to the minus here. Almost lost that. That would have been disastrous. So that ends up being 15/8 root 2. If you'd left any of them in quotient form, you'd be writing for another 15 minutes trying to come up with that. No, the reason you rationalize is all of these ended up being multiples of root 2, and my answer is multiple. And you know what? Of all of the things I run across in my whole life, this is pretty much the only reason to rationalize. And you don't run into this all that often. You have a calculator if you really need it. So leaving roots in the denominator is just fine. You do want to simplify your quotients. If you can cancel something, cancel. So a unit vector we're going to find is extremely practical over time. In fact, we're going to use it as a major, major thing next day. Now, I'm going to skip some of the geometry because I've already got that in your video. I have a video for you on today's stuff with vectors that goes over some of the geometry, the three-dimensional Pythagorean theorem, spheres and things like that. So there's some interesting but simple stuff at the beginning. For the first, let's say, quarter of the course, one of the more important lectures is what we're going to do next day. For those who've had physics or linear algebra, you're familiar with things like dot products and cross products and stuff. We're going to develop, derive, and then go over their properties next day. And I find it very interesting because I have never actually met a human being in my entire lifetime who can explain to you what cross product is and where it comes from. Everybody can do it, but they have no idea. The smartest people I've ever run into have no idea where cross product actually comes from. It's just a formula that somebody made up. No, it comes from somewhere. And dot product actually is the more important of the two in general. Cross product is the more important in this class because of the nature of the types of stuff we're going to do. Now, I'm going to go ahead and stop recording.